Hello guys, welcome in this new video. In this video we will be talking about selection sort and bubble sort, and this is a sequel of the previous video where we discussed about the master's theorem. And if you haven't checked it out, please check it out as it is useful for actually calculating the time complexity of recurrence relations. So it is a very important theorem. And I want to also point out that there are some topics in here which I will tell in every video that we do not actually need to see for actually getting, like, it is not actually needed for the exam, but you can actually use see them to enhance your knowledge. So with no delay, let's get started to this sorting algorithm, that is the selection sort, and then we will talk about bubble sort. So going to this sorting algorithm, so the first one is selection sort. So it is basically a normal sorting algorithm that is actually used to sort unsorted array elements. And in this one we actually maintain two sub arrays, one which will always contain the elements that are sorted and the other will contain the unsorted elements. And it is an in place sorting algorithm, that is that we do not require an uh, uh, um, another temporary array to actually sort, like to actually store the elements. Okay, so what we have to do is that we will, let's say we have this array. Okay, so first we will, in one go we will find the minimum element in the array, then we will actually replace the minimum with the first array. So that is, we swap the minimum with the first array element. Okay, so in this case, as 11 is the minimum, so we swap it with 64, so the array becomes this one. Then in the next iteration we again find the minimum, but now we find the minimum in the n minus 1 sub array. So we will start from the first index, this one, up to the next index. And as you know that the array elements start with 0 index, so the indexes actually are 0, 1, 2, 3 and 4. So we will now start with the first index, second index, third index and fourth index and find the minimum. And as we know that 12 is the minimum, so we will just put it there only. And after that we will now find in 25, 22, 64. As now we know that 22 is the minimum, so we will swap with 25 and put in here. Again we will check for the minimum in this 25 and 64 sub array. So 25 is minimum, so it will be put like this here only. And at last 64 is remaining, so as we do not have a sub array that is having a length more than 1, so we will stop the loop and we will get a sorted array. Okay, and this actually takes order of n square. And before seeing the code, just if you want, you can see this flowchart as well. It is just describing what just I said, and it is basically the flowchart for the code that has been written, and more generally you can say for the algorithm. Okay, so this is the code, and here as you can see that we are having two for loops, and they are incrementing one by one only, so that's why they will be having order of n square time complexity. And the swap is also there, that only takes order of 1, like that is the constant time, so we do not consider that as well for this, because adding or subtracting a constant in asymptotic analysis is not generally required. Like, we do not consider the constants here, and yeah, you can see that the um, time complexity is order of n square. There is only a constant space required because it never, like, we do not have to take much space to store any variable, and we only require the minimum element variable to store the minimum. So that's why only order of 1 is the space. And one thing to remember is that the selection sort takes the minimum number of swaps in all the sorting algorithms that require swapping. So it is an important point, and it makes order of n swaps in the first case. So yeah, this was the selection sort algorithm. Now coming to the bubble sort one. So in this algorithm, this is also a simple sorting algorithm that actually uh, like it sorts the elements in the array by repeatedly swapping the adjacent elements, okay, if they are in wrong order. So let's say we have this array and we have to actually sort it. So what we'll do is we will first take the first two adjacent elements and check which one is lesser, and if they are actually not in ascending order, if we are actually sorting them in ascending, and if they are not in ascending order, then we will swap them and put them in the first position, put the minimum in the first. And I want to say one more thing, that it is generally used in the ascending order sorting because descending order can also be done, but it requires more complexity in the code, and it generally does the sorting in ascending order. So this was the swapping. Then it will go to the next adjacent, then check whether they are in wrong order or not, so they will swap if they are. Then again to next two elements, then they will swap as they are not in the correct order, and again next two elements. So like this one pass has been completed, okay. So in this one pass, we what we will have is that at the last element will always be the greatest element, okay. So um so in first pass the last element will be the greatest. In second pass you can see that we will again go in, like we will again traverse the last sorted array, like not fully sorted, half sorted array again. So we will again go adjacent two elements one by one, and two elements at a time. So you can see the swapping will occur if they are in wrong order. Similarly, the second pass has been completed. Now we can see that the like the algorithm is sorted, but still the algorithm itself doesn't know whether the array has been sorted or not. So for this we have to again go to the like pass, we have to go for the third pass as well, where if we do not get any swap, then we consider that the elements are sorted, okay. So you can see here the algorithm written in C++, so basically the code. So as you can see, there are again two for loops, and they are having incrementing in +1 +1, by like they are incrementing at a time. So it will also be having order of n square runtime, and we can actually somewhat reduce it if we just check if the swap is done or not, because it is required to stop the algorithm for the last pass, okay. So to actually reduce this pass, we have to check whether all the elements were sorted or not. So if they were sorted, then we will stop, okay. So in this they have done this check here. So if swapped it equals to false, like here they have taken a boolean variable with false. If they had to swap any element, then the swap will be set to true and the loop will continue for the next pass. But when there is no swapping, then we will know that the elements are swapped. And yeah, the array has been sorted. Okay. And I think um, it doesn't reduce this pass here. So basically they will just still be having this order of n square complexity in the worst case, right? But the best case time complexity will be order of n, and it will occur when the array is already sorted. So pardon me for telling that it actually will reduce this pass, but it will not. But yeah, this is another approach to the algorithm for checking to reduce one more looping. Okay. So this is also an in place sorting. That means that we do not require any temporary extra array to store the elements. And it is also a stable algorithm because the key values are equal here when we actually swap them one by one. So yeah, this was the bubble sort as well. And it is actually generally used in the polygon filling of in computer graphics. And it does it the work in order of 2n, that is linear complexity is there, so it is highly used in that one. And yeah, this was it for this video, and we will meet soon in the next video as well. Okay, so till then, keep learning and keep watching.